and the slides. I hope you can see me and my slides. So shall I begin? Right, well, thank you very much for inviting me to come here. It's a pleasure to be, firstly, to be at anything at all in person, or semi-in person. It's also a pleasure to be back here in this room, I think, Festival of Mathematics, when I was talking about a rather different subject, but it will turn out, perhaps a bit later, that they're not completely divorced. So unusually, I'm going to unpick the title slide first. So the title is the same. This is the talk that was advertised, although the title is, I think, slightly different. And what I want to emphasize is that my qualifications giving this talk, I have spent quite some time over the last few years deploying my only superpower, which is ignorance. So I started off knowing nothing whatsoever about quantum computing, and I stand before you having achieved that goal of not knowing anything about it, but having asked the question, what's really going on here? And by really, I mean from the point of view of a mathematician. So what I'm going to do is to describe some of the mathematics involved, and if I appear to say things that don't make sense about the physics or the philosophy, then I should be only too happy to be corrected. My qualifications for giving any sort of talk at all are, for the IMA, are that I have just stepped down from being vice president for professional affairs there, and my current job in the third half of my career, otherwise known as retirement, is that I'm a research consultant for the Harbour Institute, which means I get to do maths more than I did in my job, so it's all good. Okay, so this is the outline of the talk. As you can see, I'm obviously not going to go into very much detail on any of these sections. There are 96 slides in this talk. The recommendation is that you should take, because Beamer counts reveals as an extra slide, so it's not 96. So firstly, a disclaimer, this talk doesn't represent the position of anyone at all.
Gender has changed.
True. In particular, it's not an invitation to tender for contracts. They made me say that. Okay, so some history from the point of view of physics, from the point of view of the mathematician. So at the end of the 19th century, classical physics was in a state of crisis. Classical Newtonian physics works extremely well for predicting medium to large scale phenomena. That's to say, from about this big, bigger and bigger. So classical Newtonian physics is very nearly good enough for landing rockets on other planets, but not quite, because classical Newtonian physics did not account for the anomalous precession in the orbit of Mercury. The orbit of Mercury doesn't quite obey Newtonian physics. So that was one crisis. Another crisis was in thermodynamics, which worked very well for predicting the behavior of steam engines, very important technology in the 19th century, but it did not account, in principle, for black body radiation. So a hot body should radiate all its energy at the most extreme limit of the spectrum, and it clearly doesn't in classical physics. And Maxwell's equations had worked brilliantly for predicting the behavior of light and electromagnetic radiation, and this new technology that was coming on stream in the 19th century called radio or wireless. But strictly speaking, with Galilean relativity, and the physical manifestation of that was the failure to discover the ether, which was an experimental failure. The Michelson-Morley experiment said either the ether doesn't exist or the Earth happens to be fixed and stationary at the center of the universe. Neither of which seemed to be a very desirable outcome. So there was a crisis. And the resolution of these crises came with quantum physics, the physics of very small things, and relativity, which is the physics of very large things. And classical physics was a very good approximation to each of these theories at the medium scale. But there is no known overarching theory that encompassed both all length and time scales. And that is still true. So mathematically then, at the end of the 20th and beginning of the 21st century, physics remains, to the mathematician, in a state of crisis. And if I was a physicist, a mathematical physicist, I wouldn't be able to sleep at night. But the important fact is that each branch works very well for predicting phenomena in the right physical arena. So we can build technologies on top of these theories. And one of the things I want to talk about is quantum technology. So the government has invested more than £500 million in a quantum technology program across 4 hubs and numerous university and industrial partners. Quantum computing is one of the topics within quantum technology. Quantum computing is what I want to talk about. One thing I want to talk about. Quantum cryptography are topics within quantum computing. And if quantum computing is a niche within quantum technology, and if post-quantum cryptography is a niche within quantum computing, then I was in charge of a niche within that niche. And so I can tell you what a niche is. It's a factor of about 20. So I got about 1/20th of 1/20th of 1/20th of that £500 million to spend at one point in my career, when I was working for Her Majesty. So let me give you a quick but not very good introduction to quantum physics. So this is why I think about it. Physical phenomena exist in a superposition of states. In other words, you do not know what state your system is in. All you know is that there's a probability distribution on the states, whatever states are. Think of states as being the sort of what really happens. And physical laws express how those probabilities evolve over time. So if there's quite a high probability that there's a ball here, and then a second later there's quite a high probability the ball is here, then another second later there's quite a high probability that the ball will be here. That is a physical law about something to do with conservation of momentum. An observation says you measure some physical property. In other words, you sample from the probability distribution attached to that property. And Heisenberg's uncertainty principle says that not all physical properties can be measured in a single observation. Another way, mathematically, that just says there are certain questions that cannot be asked. Or certain measurements that cannot be made together. So the statement, oops, should it be doing that? Better? Oh, sorry, I don't, yes. Yes, it's obligatory, I understand. The physicists will beat me up outside if I don't show you the picture of Schrodinger's cat. So Schrodinger's cat is a thought experiment. A random event is happening inside the box, which either will or will not drop the hammer on the capsule of poison gas, which will or not kill the cat. And until you open the box and, as it were, solidify, make the measurement of how many living cats are in the box, you just don't know. And the best way for me of thinking about this is to say it doesn't make sense to say that the cat in the box is alive. That's not a statement you can meaningfully make. It's the first. If you pass particles through a grid, a diffraction grid, then they come through as if they had interfered with each other as waves. And the question, is it really a particle or is it really a wave, is one of those questions that's not worth asking. The probability of finding it in a certain place behaves as if it obeys the sorts of laws that interference of waves do. But an electron is, we think, quite usefully regarded as a particle. Fridays, it's a particle. On Tuesdays, Thursdays, and Saturdays, it's a wave. And going back to the uncertainty principle, it says not all physical properties can be measured. And this is a mathematical principle. It's reflected in, for example, Fourier transform theory, which says that you can't have both the signal and the spectrum cannot be completely band limited. That's an uncertainty principle, but it's a mathematical one. It doesn't prove that the world behaves like that. The important thing is Heisenberg said, well, the world does behave like that, because to observe something, you have to interact with it. And so if we're going to find out where something is, we're going to bombard it with light waves or particles, and that will move it. So by the time you find out where it is, you will have changed the way it's moving. That's a physical statement, which says that the uncertainty principles that you find in mathematics and the uncertainty principles that we in our physical intuition suggest must exist in the physical world match. And the two things that are classical are position versus momentum, the one I've just described, and energy versus time. You can't measure the energy of a system, and you can't simultaneously measure the time at which an event took place. These are problematic for relativists, of course. And you can physically experiment to see that these are not just notional ways of thinking about things. The Casimir effect, so you take two conducting plates in a vacuum, there is nothing between them. So there should be no force between those plates. But there is, because every so often a particle-antiparticle pair pop up out of the vacuum, because there is enough uncertainty in the energy of the system to allow those things to appear, providing they appear for a short time. But the induced electric charge that that pair create on the two plates always produces a force of attraction between the plates. So the prediction of this experiment is that if you take two metal plates in a vacuum, there will be a measurable attraction between them, and there is, which suggests, therefore, that the uncertainty principle is actually physically real, not just in terms of the energy particles coming into existence, is real enough. So let me, as a mathematician, recoil immediately from all these speculative, philosophical, and physical problems and start talking about mathematics. So let's imagine that our physical system can be described by some simple set of states. For example, atoms in a crystal lattice might spin either up or down, a wild oversimplification, of course. And if we have three such atoms, which is rather fewer than you have in most crystal lattices, but about the right number for a quantum device, I may say in passing, I was slightly perturbed when I was giving this talk to some students working quantum in one of the quantum CDTs, and they were talking about their PhD work involving taking this atom and sort of lifting it up and putting it there. And I mean, I thought that was a joke, but that is actually what they do. They're building these devices at the atomic level. So this is not an completely unrealistic simplification. Anyway, we have three atoms all down. The superposition we just represent as a linear combination. That's just so they live in an 8-dimensional space with complex coefficients. And the coefficients encode the probability of the system being found in that state when you come to measure it. Those words, the mathematician, are just words that describe things you're going to do mathematically. Physicist means you're going to actually get out equipment and start pointing things at lattices. And in this example, the spins can be entangled or correlated. So if we write down this state here, it square root because the coefficients are squared in modulus to produce probabilities. But in terms of probability, that's a system that's with probability half, it will be found in the all up state, and with probability half, it will be found in the all down state. So these three atoms are in entangled states. If you knew somehow, which you can't, that one of them was up, then you would know that the others were up. And this is sometimes called action at a distance, because it means that if you know something over here, you instantly know something over here. And that can't be right. Because there is no way that information can travel from here to here instantly. Or in particular, there's no way that measuring this can cause this to happen instantaneously. The best way of thinking about this is there are only two things that can happen. You've decided, and one of them has happened, but they didn't cause each other. They were both caused by something, namely you're measuring it. And even that description, which I find satisfying, is I'm told wrong, because that is a hidden variable theory, and that is heresy to physicists. But nonetheless, entangled states exist and can be created in a laboratory. And you can build devices with them. And in fact, you can build computing devices with them. So let me talk a bit now about computing. So going back to the 1920s, 1930s, unwinding nearly 100 years, Alan Turing, very pleased to be able to give this talk in building named after him, proposed the idea of the Turing machine, an abstract model of computation. This machine has a store, and it has at any given moment it's in a state. It has a program which determines how it moves from one state to another, and what happens to the store, the data that's stored in it when it changes state. And the Church-Turing thesis is that this model precisely captures all notions of computability. In other words, everything that can be computed is something that can be computed on a Turing machine, although not necessarily very quickly. So here is Alan Turing on the left and Alonzo Church. They met at Princeton in the 1930s. And the thesis, it's a thesis in the sense that it's not a theorem, it's a statement about the notion of computability. So it's extremely plausible that this is the right way to think about computability. No one has ever thought of something that computes things differently to a Turing machine. And in particular, so here, so moving from theory to practice, Tommy Flowers, the great unsung hero of Bletchley Park and the unsung hero of computer technology, engineer, worked for the post office, was seconded to Bletchley Park, where he built the thing on the right, which is Colossus. That's the rebuild of Colossus at Bletchley Park. The first electronic, general purpose, stored program digital computer. It is general purpose, although it was designed for one particular purpose, it can be programmed to do anything that a Turing machine can do. It's a general purpose computer. And I have in fact seen a printout, probably the most valuable piece of paper in the history of computing, a printout from Colossus in which annotated by Alan Turing, in which he computes values of the normal distribution, just to show that you could calculate ordinary numerical calculations on Colossus. It's in the archive at Cheltenham. So programming and programs went back to Ada Lovelace, who worked with Charles Babbage on the analytical engine, a steam-powered clockwork computer, the first steampunk computer. And as Ada Lovelace said, the analytical engine can do whatever we know how to order it to perform. In other words, you could program it. It is true that programs can be randomized, a nuance I think that Lovelace and Babbage didn't quite capture. But the application of quantum technology to computing, I think, originated with Richard Feynman. And here is a picture of a commemorative stamp with Feynman diagrams representing particles interacting with each other. I don't think any of them is particularly associated with quantum computing, but and so what I want to do is to just say one thing about the difference between quantum computing and classical computing. In a modern classical digital computer, the store now consists of discrete bits, an awfully large number of them, 2 to the 40 perhaps, represented by physical states such as voltage or magnetism, or and these move through circuits which perform Boolean operations. For example, the NOT operation that inverts a bit, the AND operation, which gives you an output of 1 if and only if the 2 input bits are 1, and so on, all well-known stuff. A quantum computer, the store consists of entangled bits, or an ensemble of entangled bits represented by some physical states like spin. And I'm really not going to say what those physical states are because I don't know either. And they move through quantum circuits which respect the quantum coherence. In other words, they stay in a quantum state. They're not being measured and sort of instantiated as fixed states. They still retain their superposition. And these circuits perform unitary operations on these long vectors. So I showed you an 8 long vector representing 3 states. And unitary in particular means reversible. So quantum computing, paradoxically, it might seem, the circuits are all reversible. You can deduce the inputs from the outputs. And that's not true, for example, of an AND gate. The output is 0, all you know is that one of the inputs is 0, you don't know which. So not all Boolean operations are available in a quantum circuit, but some operations are available that don't have Boolean analogs. For example, the so-called square root of naught operation, which turns a 0 bit into a mixture of 0 and 1, and a state of 1 into a different mixture of 0 and 1. And this is reversible. And if you do it twice, you get the not operation. In other words, turn 0 into 1 and 1 into 0. That's got the square root of not. And there is nothing like this in conventional Boolean algebra. There is no operation, conventional Boolean operation, whose square is not. So this is, on one hand, there is a limitation on the Boolean operations that you can make, but there is an extension of what you can do jointly to bits. Now, a quantum computer is composed of quantum registers, a collection of entangled bits, and quantum circuits that process these bits. And a computation consists of preparing the states. In other words, you start off with your bits in some state with some numerical coefficients on them, which corresponds to feeding in the data. And you push them through the circuit, and the system ends up in some mixture of states, which you then observe. In other words, you read out the answer. And a quantum algorithm is a way of arranging this computation so that when you observe the state of the machine, the desired answer to your problem is the highest probability thing that you will observe. So you sample the state, which is in a mixture of probabilistic is the most likely thing to emerge. This is a very different, very, very different from classical computation, where randomization is possible, but is not intrinsic. So I may return to this if we have time at the end. So in spite of the differences,
do you mean that high probability or the highest probability?
I mean that in practice, the answer is the only thing that has a high probability. There are many, many other states, all of which have low, not necessarily the same, but much lower probability than the right answer.
And so in some sense, that's the definition of an algorithm.
Yes.
Algorithm. It has that property that.
Yes. Yes. I mean, a quantum circuit instantiates a function on states, and a useful one is one for which one particular state is overwhelmingly more probable than any other. So quantum computation, it's not quite obvious from what I've said that quantum computation, it could well be different from classical computation. It is in the way it works, but in terms of what it can compute, it is not a new paradigm in computability. In other words, the only things you can compute with a quantum device are things you can compute with the classical device, because you can simulate quantum circuit on a very much larger classical device. But it is a radically new paradigm in complexity. In other words, certain problems that are very hard for classical computation are not so hard for quantum computation. And I don't have time, unfortunately, to go into either of the classical or the quantum theories of complexity, but just to say there's a very rich theory of complexity classes. And I'll mention the two classes of problem, exponential time and polynomial time. I'm just going to use those words. Just think of exponential as being hard and polynomial as not so hard. I won't go quite so far as to say easy. So exponential time algorithms typically look like brute force search. So for example, if I just have an equation, f of x equals y, and I want to, given y, and I want to solve it for x, and I don't know anything at all about the equation, all I can do is just brute force search through all possible values of x. That is typical of an exponential algorithm. Polynomial time algorithms typically occur when you've got structure on the set of solutions. For example, linear structure, so solving linear equations, linear programming to solve optimization problems. The structure allows you to sort of sneak up on the answer bit by bit and sort of just get, as it were, get your luck in lots of little bits. That's what typically a polynomial time algorithm would look like. So there aren't many quantum algorithms that are known, more than none. First one is Grover's algorithm, and this is an algorithm that speeds up a brute force search. So if you know nothing about your equation f of x equals y, Grover's algorithm still allows you to solve that equation in a time radically small, definitely smaller than it takes you to search all possible x's one after the some state, which is a mixture of all the x's, and somehow push them all through the function and somehow select the right one. It's not quite that good, but you can think of that as being the sort of, the impetus for thinking that there might be such a thing. And what it allows you to do is to search a space of size 2 to the n in 2 to the n over 2 times square root of the search space. So it turns an exponential problem into an exponential problem with a smaller exponent. And that's really quite important. Something I'll say a bit more about is Shor's algorithm, which is a number theoretic algorithm which reduces the problem of factoring large numbers into a polynomial time algorithm. It's not known to be an exponential time algorithm. In fact, existing classical algorithms are not sub-exponential, but it is also not known to be classically a polynomial time problem either. It seems unlikely that it is, because lots of people have been thinking about it really hard. But that's the only evidence I have that no one has yet thought of a polynomial time classical factoring algorithm. But there is a polynomial time quantum factoring algorithm. And a third algorithm, which I'll call soliloquy, which was discovered by a team of researchers And to simplify things, they were working for me in around 2007, and we were allowed to publish it a few years, some years later, which is for solving a particular kind of problem, which is to do with finding short vectors in lattices, finding the hidden structure behind certain lattices. And we believe it's polynomial time, but it's certainly sufficiently likely to be polynomial time that it had an effect. So we have to, at some point, start building quantum computers, because thinking about them theoretically is great, but building them is what really people paid all that money for. So here is a picture of the National Quantum Computing Center at Harwell, except that unfortunately this building is in a superposition of being built and not built. And this is a picture of one of the states, namely the built state. A real live picture would show something slightly less impressive, but it will be up and running later this year, and it will be a laboratory with quantum computing equipment in it, at which researchers can. I think they are more interested in the physical aspects, but mathematicians have something to say there too. I'll say what that is on the next slide. So I've been talking about quantum algorithms and just assuming that we have logical qubits, in other words, quantum bits that just behave perfectly as mathematical entities, quantum circuits that just do their job of transforming quantum bits from one thing to another. Technology doesn't work like that. Practical implementations require multiple physical quantum bits, in other words, lots and lots of atoms, or some number of atoms, all spinning the right way, same way, say, to represent one logical quantum bit. And getting that to work. And so the problem is decoherence, which is like, in other words, random things happening in the world around the quantum device interact with it and force it into what looks like a classical state. You can think of it as a classical state as being one that the rest of the universe is aware of. So it's like a measurement. So maintaining quantum bits in coherent quantum states and pushing them through circuits, which are physical things, causes errors. And these are resolved by using error correcting codes to maintain the information, to maintain its integrity through the logical operations. And it actually requires new paradigms in error correcting codes. For example, things called surface codes, which are effective quantum error correcting codes. And so there's a whole theory of error correcting codes. Again, I could have talked all evening about that. All I can say right now is that the theory of error correcting codes meets practice at the point where you know something about the sorts of errors that can occur. And the sorts of errors that occur in quantum devices are different to the sorts of errors that occur in, say, radio communications or compact disc players. So we need, the existing theory is there, but you need new ideas for new codes. These are coming forward, and so surface codes are the sort of the big thing at the moment in quantum error correcting codes. They are classical error correcting codes applied to quantum circuits. So now I want to say something about cyber. So everything is cyber nowadays. First occurrence of the word cyberspace is found in the science fiction novel of 1984 by William Gibson. He very nearly nailed it. Cyberspace is a consensual hallucination of the metaverse, or rather the metaverse is what he was thinking of. But he sort of nailed it back in 1984. And you can think of cyberspace as being the internet, things happening on the internet. Here's a picture of the internet world. You'll see that rather significantly, each country is represented on the map according to the number of internet users. it has some measure of user. You'll see the biggest country in the world is China. Something we perhaps ought to take account of. You'll also notice that that really big island off the coast of Europe, the UK is we do live a lot of our lives in cyberspace now. And so the national security strategy categorized cyber attacks as a top level threat to national security, equivalent to terrorism. And so my home county of Gloucestershire's IT systems were offline at the end of last year because of the cyber attack. As you probably know, the Post Office's International Parcel Service is offline because of the cyber attack. Sufficiently archaic National Health Service systems were attacked a couple of years ago by people who encrypted all their files and said you won't get the encryption key unless you pay us a ransom. Yeah, we can't afford to have our postal services, our National Health Service, even our planning service, Gloucestershire's planning service, we can't afford to have them offline. So we have to defend cyberspace. The way the first word in the answer is cryptography. So I'm also going to give you a brief history of cryptography. Very brief. Traditional cryptography, otherwise known as secret key cryptography, probably invented by, well, certainly invented before Julius Caesar, known to Julius Caesar. The so-called Caesar cipher is the famous, write down the letter 3 on in the alphabet from the one you mean. It's the state of the art in 55 BC. Current state of the art is one-time pad, and electronically there are symmetric key systems or secret key systems in use in mobile phones and computers, internet. Modern cryptography, sometimes called public key cryptography, was invented by my erstwhile boss, Cliff Cox, in 1972, as a result of a challenge by his boss, James Ellis, who said, can we dispense with the secret key? Can we do encryption without the secret key? And the answer is yes. And the system that he invented was published independently, but a little later by Rivest, Shamir, and Edelman, which is why it's called RSA cryptography, not Cliff Cox cryptography. And it and its descendants, like Diffie-Hellman, which was invented by Cliff Cox's colleague Malcolm Williamson, and these are used in things like TLS and SSL, which are jargon words for the thing that happens when your browser bar changes color and the little flashy padlock comes on. And what I want to allude to in this talk is postmodern cryptography, quantum and post-quantum cryptography, by which I mean quantum cryptography for the post-quantum computer era. Quantum computers are coming, and in 2006 or so, I said that they would be here in 2017, and which was not a bad shot at all. And someone said to me at the time, do you mean that someone will build a quantum computer in 2017? And I said, no, but in 2017, there'll be so much hype that we'll have ministers on the phone saying, this quantum computer thing, what's it all about then? And that was pretty well right. I mean, it's 2018 actually, but we've got a lot of hype, but the hype is real. The hype is real. The hype is about a real thing that is actually happening. What it does is it reduces the level of security of things that we care about, which we tend to measure in terms of not, is this secure binary, yes or no, but how long would it take someone and how much money would they have to spend to get access to something we don't want them to have access to? How long can we protect our secrets for? And you might say 50 years, sometimes even as long as 100 years. And I have to say, that's a really bizarre calculation to do. What is technology going to be like in 100 years' time? I have no idea. What did technology look like 100 years ago in computing? They were hand-cranked adding machines. So the difference between a hand-cranked adding machine and this, what's this going to look like in 100 years' time? We don't know. So we have to keep track of it. And quantum computing has shifted a lot of those timelines, because we know quantum computing is going to happen within 100 years. So traditional cryptography is about many things: privacy or confidentiality, authentication, in other words, making sure, think of checks. Do you think of checks? Maybe people don't think of checks. Contracts. You sign a contract. Only you can sign the contract. Integrity. Once you sign the contract, you don't want people to change the terms and conditions. Non-repudiation. You don't want somebody to sign a contract with you and then later turn around and say, oh no, I didn't sign that. Traditional cryptography achieves all of these things. Part of the paradox of traditional cryptography was always, how do I get the secret that I need to make the thing work to the other person? Because if I know how to do that, I have a secret, secure channel. So why don't I just do that? And it's, as in so much in life, it's all about timing. You know, maybe I can meet you, once, and then we can't meet again. Here's a Second World War time secret key distribution device. It's a piece of silk printed with random numbers in washable ink. It's handkerchief. At least when you've washed it, it's handkerchief. But until you've washed it, it's a pad that allows you to communicate by radio with your with London. Typically, it was issued to pilots, so they could, if at all possible, they could say where they'd been forced down before they were captured. And I won't go on about chain of trust. And I don't think I will mention this either, because I want to get on to postmodern cryptography. So what are the two things going on in cryptography? Well, firstly, among the active areas of research are privacy preserving or privacy enhancing technologies. So the Royal Society actually published a report on that yesterday. These are ways of using personal data to get useful results en masse without revealing anything about that's private. So this is really hot ticket item because the National Health Service has got huge amounts of extraordinarily valuable data about effectively the entire population for the whole of their lives. That's a fabulously valuable resource if it can be mined without compromising the privacy of you, me, and everyone else about our medical records, which individual patients in the National Health Service are quite rightly extremely concerned about. So ways of doing that, and this is a sort of cryptographic problem. It's very different from this sort of old, how can I do this secretly? I mean, it's got lots of questions about how can I protect, what does privacy even mean? Again, I think it has to be in this, not is this data private so much as would somebody have to spend more time and money than it could ever be worth to discover, say, your personal medical record, your medical record. It might be doable in principle, but you might nonetheless feel that you were adequately protected. You might not, that's your choice. And the other active area of research is post-quantum cryptography, because, as I've just mentioned, Shor's algorithm means that quantum computing will completely change our view of the security of internet communication, which relies very heavily, to a very great extent, on the difficulty of factoring large numbers. And one of the things we have to do is to understand exactly when that's going to fall off a cliff. But the American National Institute of Standards ran something which was not a competition, they said, but actually it was a competition to come up with new cryptographic schemes. And there was something like 80 entries. And the way this format works is that everyone's trying to win the competition, brackets, but it's not a competition, which means that every proposal has got at least 79 people who are desperate to find something wrong with it. And that's a really good way of weeding out bad ideas very quickly. And that competition, not a competition, has come to a decision. And it turned out that the two classes of proposal are systems where there is some hidden secret within your system which allows you to do certain things much faster than anyone else. And that's exactly the same property that RSA had. Knowing the factor certain equations much faster than anyone else. The soliloquy work was about finding hidden structure. Turned out that hidden structure could be found by a quantum computer, but not by a classical computer. So soliloquy wasn't even in the competition. It was we knew 15 years ago that we weren't going to propose it. And it turns out that all the successful candidates in the NIST not a competition are based on error correction in two fields. One is in the traditional theory of error correcting codes. So error correcting codes come into the picture in a completely different way. Correcting errors in error correcting codes is something you want to be able to do very quickly. And so there's a whole theory, very rich theory of codes for which errors can be corrected quickly. And typically such codes have an algebraic structure. And if you conceal that structure, then other people can't correct errors nearly as quickly as you can. So you send your message, you take your message, and then you garble it. And then you send it to the recipient. The recipient knows how to fix the errors because he has access to the hidden structure, but the eavesdropper doesn't. All he sees is a garbled message, and it's hard for him to reconstruct it. And the other class of problems are the continuous analogs. In other words, instead of being finite structures over a finite field, they are lattices in some Euclidean space of very large dimension. So the problem there is I have a lattice, I have lots of discrete points in Euclidean space, I have a real vector, and I want to find the nearest lattice point. And that is the message is on the nearest lattice point. But I can't find it without knowing this hidden structure. I just do want to mention quantum cryptography. It's not a phrase I like. We prefer to call it quantum key distribution. So this uses quantum technology to communicate securely. But what it really does is it's best thought of as a very, very, very good tamper-proof cable. Right? It's a really, really strongly armored cable between 2 points. And that makes it the strongest link in the chain. And if you rely on the strength of the strongest link in your chain, then you're looking in the wrong place, which is why my colleagues didn't like it. But I will very briefly describe how a version of how it works. This is the classical version. This is quantum key distribution 1.0, which could have been done in the 19th century, but wasn't. you randomly select two axes, two orthogonal axes, which are either horizontal vertical or both diagonal. And then you transmit your bits are polarized light, polarized photons, which are either polarized that way or that way. That is one choice of bit, or polarized that way or that way. But you don't tell the recipient which way you've chosen. They just have to guess. So you just keep on sending that bit lots of different ways and hope that sooner or later, they'll make the right guess. They'll get the message, literally. If the eavesdropper intercepts that and retransmits it, they have no idea, which they can't do any better than the recipient in reading the message. But what they really can't do is retransmit it. So if your message is being tampered with, the recipient will discover that he's seeing garbage. So he knows that someone's listening to the message. And you can do that in the quantum world as well with entanglement, and I'm just not going to say any more about that. Again, another entire talk there. I mean, this is great. This is great technology. There are people who have got a pair of entangled bits, one of which is on the ground and the other which is in space. So they can communicate one bit to their satellite. Well, it's just a matter, from there on, it's just a matter of scale. They can maintain entanglement on bits that are hugely separated. But National Cybersecurity Centre, which we used to work with, don't recommend it because, as I said, their view is that you're looking in the wrong place. Soliloquy, we don't recommend either. We never did recommend it. But it was an example, and a very interesting one to us, of a case where a quantum attack was found on a potentially quantum resistant system. And it makes me feel a little unhappy about some of the others, because it's in this whole looking for hidden structure. In summary then, designing quantum resistant cryptography is hard. And it took, one of the reasons GCHQ decided to publish work on soliloquy was they realized that one group of people, however smart they were not going to outpace the rest of the world. So it was better to work with rather than against the rest of the world in order to get proper assessment, because there's a lot of hype, an awful lot of hype. Have I got? Yes. There's a lot of hype around quantum computing, and in particular, when you see news stories that say, this, that, or the other company or country has got a quantum computer with this, that, or the other number of qubits. The first question to ask is, are those logical qubits or are they physical qubits? I don't believe anyone's got more than a handful of logical qubits to work, but to get a handful of logical qubits, you need dozens and dozens of physical qubits. So when someone says we've got 57 physical qubits, I think they might mean they've got 3 logical qubits. Quantum computers with 8 logical qubits exist, and although I personally have never played with them, I've spoken to people who have. But that's a long, long way from the number of bits that are in something like this. But nonetheless, it's got to happen, and it is happening. And the important takeaway for mathematicians is that, as you would expect, these new technologies not just take bits of maths off the shelf and say, thank you, historical mathematicians of the 19th and 20th century, for providing us with everything that we wanted neatly packaged. Because that just doesn't happen. The ideas for how to solve these problems may be there, and the people who know how to solve the problems are there, but they're mathematicians. And the important thing for me is that there is important interest in new mathematics to be done in areas where you might not have expected it. Minkowski's work on high-dimensional lattices, not obviously of much practical importance. The theory of error correcting codes, well, it was obviously practically important, but turns out that the new class of problems are different to the old problems produced by space probes and compact disks. So mathematics will continue to be at the heart of this enterprise in the postmodern era, just as it has been since Alan Turing and Tommy Flowers worked together at Bletchley Park, 75, nearly 80 years ago now. Thank you very much. Are there any questions? And I will now attempt to get new technology to work by looking at the questions. I don't think, well, I thank the questioner for his suggestions. I personally am not able to propose people for Nobel Prizes, but your comments are taken into consideration. Thank you very much. Are there more questions coming up? Do I anticipate quantum computers being used to solve unsolved problems? I think the answer to that has to be yes, if only because classical computers turned out to be important in solving problems. But I don't know how.
Just a quick question.
Yes,
Richard. You say there's this building that's going to have quantum computers on site. What physical materials are used in current quantum computers?
Okay, so for the benefit of the audience, Stephen asked what does the physical instantiation of a quantum computer look like? What's it made out of? And the answer is, I'm afraid, it depends. There are something like 4 routes to quantum computing. Typically, a quantum computer consists of a crystal of some kind at an extremely low temperature.
So why do they have to be low temperature?
Because thermal fluctuations destroy the quantum states.
So when you say is this below 4 Kelvin?
Yes, well, somewhere on this laptop, I won't trouble to find it. I have a picture of the fridge of a quantum device. The people who make it say that it's the coldest place in the universe. It's of the order of millikelvins.
Really?
Yeah, which is way colder than outer space, which is at around 3 Kelvin. Microwave background radiation, I understand. I'm repeating these words as if I knew what they meant, but okay, question, if you can brute force traveling Selson problem using quantum, well, yes, I guess it's always true that there is a feeding frenzy around quantum computing and quantum algorithms, which may distract us from looking for good classical algorithms. That's certainly true. On the other hand, in the other direction, so a few years ago, a graduate student was set the problem of finding a quantum algorithm to solve the Netflix recommender problem, which is a problem in linear algebra, it turns out. And it turns out that that quantum algorithm can be classicalized. In other words, a new classical algorithm was found for solving that problem as a result of trying to think of a quantum algorithm for solving it. So, you know, the options are still open, I think. Do I have a sense of the speed increase? That's an undetermined quantity, I'm afraid. I don't know. I mean, quantum computers are so much in their infancy. It's like it's a piece of string problem. Are the different complexity classes for quantum algorithms that don't fit into our current definition of P and NP? Absolutely, yes, there are. There's a whole hierarchy of quantum complexity classes analogous to, but different from, the hierarchy of classical complexity classes. Have I experimented? Not me personally. an interesting cryptographic circuit on current hardware. I think the clue was in, there aren't enough bits. How are quantum algorithms coded? There's a whole, there are companies that are now producing compilers for quantum computers. So Riverlane, for example, in Cambridge it's a company that you go to them and you'll buy a quantum compiler from them. Can compilers for conventional languages be targeted quantum backend? I don't think that's how it works, but I don't know. Who do I expect to look at quantum cryptography? Well, I think it's the NIST competition is an example of how this works. If you motivate people just a little, they will look at interesting problems. But you do have to give them a bit of motivation, you have to give them a bit of freedom, you have to give them a bit of a sort of lubrication around their, fit it into the day job. Can you thread and multiprocess quantum computers? Not quite sure what that means. Quantum computers are sort of intrinsically multi-threaded. I think I have to say I don't know. How did I initially get into a career in cryptography? By being a pure mathematician. Surprising, but true.
Can I ask a question about the energetics? Because particularly with sustainability in mind, if one's working at micro Kelvin, how expensive is it? And will it continue to be?
Those fridges are pretty big. Yeah. I couldn't give you numbers, but yeah, it's currently the energy required to keep the thing cold. So I guess that's of course, the ideal solution would be room temperature superconductors would be part of it, I guess. But yeah, it's probably going to be, I'm not going to say unsustainable, but the footprint is going to be pretty big for some time to come. But I really want to pay tribute to the technology involved in doing electronics at this sort of milli-Kelvin scale is already great. But then you have to get the signal from a milli-Kelvin world up to a 290 Kelvin world, through bits of wire that somehow are conducting electrons or something one way, but not conducting heat the other way. So that's pretty remarkable stuff. So I guess that the sustainability is going to be ramped up over time, but it's currently pretty expensive. I mean, when you consider how many bits there are, what more sort of it.
On the moon.